All right, now the nature of liquids. On the previous slide, I talked about vapor pressure, what it means. Now we're going to talk about comparing specific liquids and their nature in regards to their vapor pressure. Now, ignore the colors, the difference in colors. This isn't really too important. The difference in colors isn't really too important to what we're talking about today. Now, on the left, you can see the gray or white circles. These are supposed to represent certain molecules, let's say, certain molecules of liquid, let's say water for now. So the model on the left compared to the other models, this model has a liquid that has a strong IMF. This is intermolecular forces of attraction. Uh, it should have been covered in Regis chemistry, the difference between intermolecular and intramolecular. To give a short summary, intermolecular force of attraction, this occurs between specific molecules, while intramolecular force of attraction, they occur between atoms in a molecule. So let's say I had water, H2O, in the gas form, or it doesn't really matter which form. But let's say gas form, water vapor. The attraction between the hydrogen molecule and the oxygen molecule, this would be considered intramolecular. This is a covalent bond. Now, if we talk about intermolecular, I'm talking about the force of attraction between the oxygen molecule, the oxygen atom from one molecule of water to the hydrogen atom of another molecule of water. This bond, this is referring to the intermolecular force of attraction, which is dipole-dipole in water's case because water is a polar molecule. Now, the model on the left has a stronger intermolecular force of attraction. This means that the force of attraction between each molecule of water is very strong. This means that it's going to take more energy to make this liquid evaporate, which is why it has a higher boiling point. Now, the model to the right, this is a representation of a gas that has a weak intermolecular force of attraction. This means that the force of attraction between these molecules is very weak, which means it doesn't take much energy for these liquids to boil and evaporate, which means they have a lower boiling point, and it means that they are what you can call volatile. Now, the nature of liquids. This is similar to what I talked about on this slide, but now we're looking at it in graph form. Now, if you look on the y-axis at about the 100 mark, you're going to see a dashed line that says 101.3 kilopascals. This line, this is the standard pressure. Now, if we look along that line where it intersects with the water line, you can see that it meets at the point where the temperature is 100 degrees Celsius. This is referring to the boiling point of water. Now, let's say where we are in this room right now, this is at a standard pressure. This means that water will boil at 100 degrees Celsius because the vapor pressure of the water at 100 degrees Celsius matches the atmospheric pressure of my room, 101.3 kilopascals. Now, because this matches, water will start to boil. Now, if we compare to the other liquids that are on this chart, propanone. Propanone will boil in a standard pressure room at, let's say about 56 degrees, 55.5, somewhere around there. Now, propanone boils at a much lower temperature, has a lower boiling point than that of water. And if we look at this previous slide, if it has a lower boiling point, it means that the intermolecular force of attraction between each molecule, they are weaker. That means they're more volatile. They're more likely to have a higher vapor pressure because they are not able to bond with each other as well and stay a liquid. They're going to be more easily separated into a gas and form this bigger space between the molecules. Now, this means that propanone is much more volatile than water, more volatile than ethanol, and more volatile than ethanoic acid. And the same is also for the case vice versa. Water is much less volatile than propanone and much less volatile than ethanol. But it's not as water is more volatile than ethanoic acid because it has a lower boiling point than ethanoic acid. Ethanoic acid is the least volatile substance on this chart. Does anybody have any questions about this? Also, I should have mentioned this earlier. I will be posting these slides later in case if you missed this in any of your notes. I hope you are taking some notes of your own because that is how you ultimately study and how you can absorb this knowledge better. Or maybe an iPad, I don't know, however you prefer to take your notes. All right, now, Raoult's law. This law can be used to determine the new vapor pressure to a certain solution after a solute is added. So going back to my previous example, let's say I had a bowl of soup, right? But then I decided to add even more salt because I thought it was too bland. The vapor pressure of this new solution, this new soup, has changed, and we can use Raoult's law to figure out how much that is actually changed by. Now, the formula is you take the mole ratio of the solvent and multiply this by the pressure, the vapor pressure of the solvent. Now, if you remember earlier, solvent is the liquid, it's the water of a solution. And on the screen right now, you can see that X solvent, this is just a symbol for the mole fraction. And the mole fraction of a solvent, this is just taking the moles, the number of moles of the solvent, and you divide this by the moles of the whole solution. Not just the liquid, but you also need to include the solute too, the salt that you're adding. And from there, you can figure out the mole fraction. All you do is multiply that by the original pressure of just the solvent, and you can figure out the new vapor pressure of the solution. Now, I am going to ask everyone to now please answer the question that's at the bottom. At 20 degrees Celsius, the vapor pressure of water is 17.5 torr. If 2.00 moles of sugar are added to 8.00 moles of water, what is the new vapor pressure of this aqueous solution? An aqueous solution is just a solution where the solvent is the water, where the liquid in this solution is just the water. That's it. And you are going to see that term a lot when you come across chemistry problems. The answer is 14 torr. Now, one error that you may have made is that when you're calculating the mole fraction, you divided the number of moles of the solvent by the moles of, let's see. Actually, I think I may have made a mistake here. Let's see. I actually made a mistake here. Yeah, there we go. I'm sorry. That was not 0.5 times 17.5. It's supposed to be 8. Yeah. But going back to it, you take the mole fraction, which is the number of moles of the solvent. That's 8 moles of water. And you divide this by the number of moles of the whole solution. And if you add 2 moles of sugar to 8 moles of water, that means the number of moles of the total solution is 10 moles. That is 8 over 10. And from there, you multiply this by 17.5 torr, and then you ultimately get 14 torr as the vapor pressure of the solution.